Okay, so hi everyone, my name is Parvathy Prem. Our group is based at UT Austin and PSI, and we've been using computer simulations to try and better understand the processes that deliver volatiles to lunar pole traps in the aftermath of the comet impact. So a number of observations suggest that there could be water present in permanently shadowed craters near the lunar poles. And among the several mechanisms that could deliver water to the lunar surface, our focus is on comet impacts as a source for cold trap water. We know that a large amount of cometary material has impacted the moon over the last 4 billion years, and previous analytical and numerical models have estimated that a significant fraction of this could remain gravitationally bound after impact and make its way to the polar cold trap. The main challenge in modeling this problem, though, lies in the range of spatial and temporal scales involved, because the transport processes that dominate in the post-impact scenario occur on a truly planetary scale and take place over the course of months. So because of this, most previous studies have been limited to looking at volatile retention in the near field and the short term, or to looking at global transport and loss processes in the late-term collisionless limit, where molecules migrate through ballistic collisionless hops. We use a hybrid SOVA-DSMC method, which I'll describe in the next slide, which has the advantage that it can handle both of these limits, as well as model the transport processes that dominate during the intermediate stage. Our simulations consider the impact of a comet composed of pure water ice at a number of different impact angles and different impact speeds. We implement a very basic diagonally varying surface temperature map with 7 cold traps, 1 at the North Pole, 6 at the South Pole. Molecules that strike the lunar surface reside there for some amount of time that depends on the local surface temperature before they hop off. And molecules that are in the sunlight may be subject to photo destruction. The hybrid approach that we use basically relies on the use of 2 different codes to simulate different aspects of the problem. We use the SOVA hydrocode to simulate the melting and vaporization of ice and rock immediately upon impact. And we then use the direct simulation Monte Carlo method, which is a particle-based technique, to simulate the expansion of the vapor plume that's generated out into the near vacuum of the lunar atmosphere. So as you can see from this schematic, a comet just about this big gives rise to a truly gigantic plume of water vapor that expands out into space. And this expansion takes place in several stages. Here, you're looking at contours of radial velocity in the plane of impact during the first 30 seconds after impact. And at this stage, you can see that the vapor is mostly just moving radially outwards from the point of impact at explosive speeds that are much higher than the lunar escape velocity. At later times, the outflow begins to slow down, and we start to see vapor falling back to the lunar surface. As vapor begins to fall back, we find that we can draw a boundary that separates the infalling vapor from the vapor that's still moving away from the surface of the moon. And as time progresses, more and more vapor begins to fall back from higher and higher altitudes. And so the size of that fallback envelope grows, as you can see in this snapshot, which shows density contours in the plane of impact 6 hours after an impact at the North Pole. Apart from the fallback envelope, the other striking feature of this characteristic sort of flow field is the convergence of streamlines antipodal to the point of impact, as the vapor cloud expands to completely surround the moon. And if we zoom in, we can see that that antipodal convergence has the effect of channeling vapor to the lunar surface at the antipode. And there's also a noticeable difference between the night side and the day side of the moon. This is because the night side surface is cold enough that any vapor falling back effectively remains frozen until the dawn. But vapor that falls back on the warm day side is relatively more mobile. And so because of the vapor pressure supplied by that day side atmosphere, the cold high-velocity fallback shocks and is diverted into low-altitude, relatively dense winds, which transport vapor in accordance with the global pressure gradient, which in this case are from north to south and also from day to night. As we continue our simulations even further in time, there's less and less vapor left at altitude, and so the intensity of the fallback diminishes with time. In the next few snapshots, I only show the portion of the water vapor that's within 100 kilometers of the lunar surface. So here you're looking at that near-surface atmosphere 24 hours after an impact at the North Pole. And at this stage, you can see that the atmosphere is thinned out considerably, but because of the antipodal channeling that I spoke of, the atmosphere is also relatively denser around the antipode. And again, as we continue our simulations over the next few hours and days, we see that the atmosphere at altitude becomes more and more rarefied, and the antipodal effects ultimately vanish. The flow then transitions into this late turn stage, in which the densest part of the atmosphere is confined to along the dawn terminator. And it actually rotates with the dawn terminator as it's replenished by night-side frost that sublimate as the sunlight strikes them. We can also look at the evolution of these night-side frosts with time. Under our simple temperature model, the day side is too warm for any water at all to condense out, which is why you're only looking at half of the moon in this video. But we can see that for an impact at the North Pole, as we'd expect, because of the antipodal effect and the dayside winds, the thickest frost deposits are observed around the point of impact, around the antipode, and also along the dawn and dusk terminators. And because the fallback decreases in intensity with time, this relatively thick band of frost is preserved along the initial dusk longitude. So this video doesn't show the cold traps themselves, but throughout all this, we do keep track of the amount of water that lands up at the polar cold trap. In this plot, the big black line shows the amount of cometary material that's gravitationally bound to the moon 30 minutes after impact, which is when this graph starts. The orange line keeps track of the amount of water that's lost, either because it's totally destroyed or because it crosses the heliosphere of the moon. And the purple and blue lines show the amount of water that's cold trapped at the South Pole and the North Pole, respectively. So this impact was at the North Pole of the moon, and we can see that the antipodal effects have the interesting result of leading to thicker deposits of ice at the South Pole because that's antipodal to the North Pole. If we vary the location of impact, we do find that the relative thickness of the South Polar and North Polar deposits varies, but the total cold trapped amount remains approximately the same because the transport and loss takes place over such a long time scale. So far, I've only spoken about the portion of the vapor that expands explosively from the point of impact. But there's also a significant amount of cometary material that's more thoroughly mixed with the pulverized rock in the bottom of the impact crater, and thus takes longer to leave the point of impact. Currently, we model this component as a bubbling puddle of mud, if you will, from which water sublimates at an exponentially decaying rate. So the migration of water from that puddle of mud is shown in this sequence of figures from Benedict Stewart's thesis. This is at 10 minutes, 1 hour, and 1 day after the release begins. And you can see that the flow field produced by this is qualitatively quite different from that produced by the explosive expansion flow I spoke about previously. And the amount of vapor that goes into the explosive plume or goes into the slower sublimation depends on various impact parameters.
You have about 1 minute left.
Okay. And in order to quantify the amount of water that's delivered by the historic impact flux, we need to get an idea of how sensitive volatile retention is to various impact parameters. And so we're in the process of running a parametric study to try and figure this out. Here I'm comparing 3 cases from a baseline case in which the comet impacts at 45 degrees from the horizontal at a speed of 30 kilometers per second, and also a steeper case and a slower case in cases 2 and 3. And so the most interesting thing about this from the point of view of volatile retention is that in the same amount of time, the vapor plume in the more oblique, higher speed case has traveled a greater distance, which means that this plume has a higher kinetic energy and more of it is likely to escape. We can quantify those trends by looking at the outflow from the point of impact. And here we have the cumulative and instantaneous flux across the red hemisphere shown here, which is the interface between our two codes, as a function of time. And you can see 3 different trends corresponding to the 3 different impact cases. And if we measure the amount of cometary material that's gravitationally bound 30 minutes after impact, we see that that's the least for the more oblique, higher speed case. It's around 28%, considerably higher for the steeper impact, and somewhere in between, though we're still running this case to completion, for the slower impact. And so, as a preliminary conclusion, the impact angle seems to influence volatile retention more than the impact speed. But we're still trying to get more data points so we can quantify those trends better. And just to conclude really quickly, to return to the questions we set out to answer, given a comet impact, what can we say about the associated volatile fallout? And the main takeaway from our work is that the post-impact transport processes that dominate are qualitatively very different from collisional transport through ballistic hops. We have pressure-driven winds and antipodal effects, which can lead to preferential or enhanced deposition of volatiles at particular cold traps. So how much water could comets have contributed to the lunar volatile inventory? That's something we discussed to some extent in a 2011 paper by Benedict Stewart et al., and we're working on the parametric study to quantify that further. In terms of future work, we're looking to have a more realistic comet, possibly with more species and rock as well as ice, incorporate some of the incredible data that's come back from LRO in terms of temperature and topography. There's also some additional physics we can include, and I'm hoping to start work on some of these in the near future. Thank you very much.
Very good.
Thank you so much. And Parvathy, we remember that you were a poster winner a couple of years ago in our competition. And so we're glad to see that your career is going along so well. Excellent talk. I know we.
I think there's a question from Catherine Niche. Did you take into account the different thermal environments at the North and South Pole?
So right now, the temperature map we use, the temperature just depends on the distance from the subsolar point. So we do take into account that the temperature at the poles is less somewhat, but it is a simplified model, and we haven't incorporated more detailed information.
Got it, right. Carly asked a question, have you considered surface topography in your models since it would lead to local cold trapping, at least for the large craters, and delay the transport of volatiles to the poles? I think that's sort of similar to
and the answer to that is not yet, but we have put in a proposal to look at that kind of thing. And, you know, we think it would be very interesting to look at how the wind and the antipodal effect interact with the topography and perhaps produce some of the local differences that we see between the cold traps. So we do want to put topography in, and we're probably going to start work on that soon, given this funding.
Wonderful.